Hello everyone, I am Ömer Burak İstanbullu and I am an assistant professor at Department of Biomedical Engineering in Eskişehir, Osmangazi University. Let me share my presentation screen with you. Well, here we go. My presentation is going to be about smart and nanomaterials in biomedical applications. If a material undergoes structural change over time in response to variations in environmental stimuli, it is referred to as a smart material. Smart materials are expected to perform some functions, including sensing the environmental change, undergo structural change in response to these changes, reacting to these changes accordingly. In biomedical applications, the environmental change includes stress, strain, temperature, humidity, pH, electrical field, or magnetic field. These changes, depending on these stimuli, smart materials may exhibit shape transformation, elongation, contraction, change in the viscosity, light emission, color change, or induction of electrical current. Smart materials are generally classified into two main categories based on the environmental stimuli and material structure. Smart materials classified by environmental stimuli include piezoelectric materials, magnetoelectric and magnetostructive materials, thermally responsive materials, light-sensitive materials, pH and chemical responsive materials. Smart materials classified by material structure include shape memory alloys, shape memory polymers, hydrogels and biomaterials, magnetic nanoparticles, electrochemical responsive polymers. For example, when mechanical stress is applied to a smart material with a piezoelectric structure, it generates an electric charge, producing an electric current. Likewise, when light energy is applied to a light-sensitive smart material, chemical or physical change can be observed. Smart materials with shape memory alloy or polymer structures have the ability to return to their original shape when exposed to a specific temperature. In biomedical applications, this temperature is typically around 37 Celsius degree, which corresponds to the body temperature. In smart biomaterials containing magnetic nanoparticles, exposure to a magnetic field can induce heating or displacement. Such behavior makes these materials suitable for targeted drug delivery applications. This table summarizes the classification of smart materials based on their type and intended application. It presents the smart behavior associated with each material type and highlights specific biomedical applications. For example, nitinol, a thermally responsive material, undergoes shape transformation in response to temperature change and is therefore used in the design of shape memory stents. Additionally, azobenzene derivatives, which are light-sensitive materials, undergo physical and chemical changes upon exposure to light energy and are employed in photodynamic therapy for cancer treatment. The application areas of smart materials based on their material structure are summarized here. For instance, polypyrrole and polyaniline structures, which exhibit sensitivity to electrochemical change, are utilized in the design of biosensors and neuroprosthetics. Due to their ability to undergo volumetric or conductivity change under the influence of an electric field, these materials can generate electric signals capable of stimulating the nerves. Well, nanomaterials are defined as materials with at least one dimension in the 1 to 100 nanometers range. Their surface area to volume ratio is extremely high. This results in enhanced cell interaction and biological interaction, higher mechanical strength, potential for functionalization to create responsive or targeted systems. If we have a look to the applications of nanomaterials in biomedical field, nanofibrous scaffolds can mimic the extracellular matrix, promoting cell attachment and proliferation, aiding tissue regeneration. To be used in biosensors, nanoparticles enable early and sensitive diagnosis, target-specific binding, and enhances detection capabilities. On the other hand, silver nanoparticles disrupt bacterial membranes. They are used on implants and wound dressing to reduce the infection. Electrode surfaces modified with biocompatible nanocomposites improve sensitivity and selectivity in bioelectronic devices. Furthermore, MRI contrast agents using iron oxide or other nanoparticles, fluorescent nanoparticles, help in real-time imaging at cellular levels. We can divide the nanomaterials into four main groups depending on dimensionality, morphology, state, and chemical composition. Depending on dimensionality, they are grouped into zero-dimensional, one-dimensional, two-dimensional, and three-dimensional structures. Nanoparticles can be metallic, ceramic, or polymeric in origin. Their small size and tunable surface properties make them highly functional in biomedical fields. Gold nanoparticles commonly used in optical biosensors, especially for cancer diagnosis. In photothermal therapy, they absorb light and convert it to heat, selectively killing cancer cells. Silver nanoparticles are known for their strong antibacterial activity. They are widely used in medical device coatings and wound dressing to prevent infections. Silica nanoparticles, on the other hand, act as carriers for controlled drug release, improving treatment precision. They also serve as fluorescent markers in cell imaging and diagnostic applications. Carbon derivatives like graphene and carbon nanotubes are widely used to their excellent mechanical strength and electrical conductivity. Graphene and graphene oxide structures improve cell adhesion when used on cell culture surfaces. The structures can be integrated into electrochemical biosensors for sensitive detection. They can also serve as scaffolds in tissue engineering, supporting cell growth and regeneration. Carbon nanotube structures are used as biomaterial scaffolds, particularly in muscle and nerve tissue engineering. Their electrical conductivity promotes better communication with nerve cells. They also function as carriers for DNA and proteins, enabling targeted drug delivery. Electrospinning produces nanofibers that mimic natural tissue structures. In cell culture environments, these nanofibers promote cell adhesion and proliferation. So this supports the tissue growth. Nanofibers and nanocomposites are used in wound healing and biodegradable dressings. They help reducing the risk of infection while being safely absorbed by the body. For bone tissue engineering, nanofibers reinforced with hydroxyapatite-like structures provide mechanical strength and further support the bone regeneration. Magnetic nanoparticles can be manipulated remotely using an external magnetic field. Here, MRI contrast agents as iron oxide nanoparticles enhance image contrast in MRI scans for better diagnosis. Magnetic nanoparticles enable magnetic hyperthermy, where targeted tumor cells are heated and destroyed without harming healthy tissue. They are also used to capture specific biomolecules, so magnetic nanoparticles improve sensitivity and specificity in biosensing devices. In drug delivery and tissue engineering, the porous structure of nanomaterial is crucial for these biomedical applications. For instance, in drug carrier systems, these nanoporous structures enables controlled and targeted drug release, improving treatment effectiveness and reducing side effects. The nanoporous architecture supports cell adhesion and growth, promoting tissue repair and regeneration. the application of specific nanomaterials and the main purposes are summarized in this table. For example, graphene and carbon nanotubes are used in tissue engineering for promoting the cell adhesion and tissue regeneration in scaffolds. On the other hand, silicon nanoparticles are utilized as a drug carrier in controlled drug release. Antibacterial feature of silver nanoparticles makes us to use them in wound healing. Smart materials respond to different types of stimuli, which can be grouped as follows. One of which is physical stimuli sensitive nanomaterials. They react to change in temperature, electrical or electrochemical signals, light, and magnetic field. Chemical stimuli sensitive nanomaterials respond to pH variations and redox conditions. This enables environmental specific behaviors. Biological stimuli sensitive nanomaterials, they are sensitive to biomolecules like glucose or enzymes. They are useful in biomedical sensing and controlled drug release. Some materials are dual or multiple responsive, meaning they react to more than one type of these stimulus, enhancing their functionality and precision in applications. This table summarizes various utilization of smart nanomaterials having different stimuli sensitivity. For instance, while electrically responsive iron oxide and polyaniline nanostructures are used in antimicrobial or drug delivery applications, when the iron oxide is combined with methoxypolyethylene glycol polylactic composite, they can be used as an MRI contrast agent. Electrically responsive polymers change their size or shape when exposed to an electrical current. They convert electrical energy into mechanical motion via ionizable groups. Their application includes targeted drug delivery. Here, the electric current disrupts hydrogen bonds, altering the pH and causing polymer degradation. The drug release is controlled through electrophoresis, diffusion, and erosion of electrodegradable polymers. In muscle actuator usage, these structures mimic the muscle contraction by responding to electrical stimuli. In energy conversion systems, they convert electrical signals into mechanical work or vice versa. Types of electrical sensitive polymers include current sensitive, which are hydrogels, conductive polymers, thin film coatings. Voltage sensitive designs, which are dielectric gels, elastomers, nanoparticle-based drug delivery platforms. These nanomaterials respond to electrical or electrochemical stimuli to control drug release or material behavior. They are made of natural polymers like alginate and chitosan, and synthetic ones like polyaniline and polypyrrole. Polyelectrolytes can swell or shrink when exposed to an electric field. Abedian et al. Developed nerve probes with polymer nanotube coatings for electrically triggered drug release. As seen in the image on the right side, Ha et al. Designed the electroresponsive hydrogels combined with photothermal therapy for brain tumor treatment. The different fluorescent images for both on and off conditions applied with electrical stimuli influence on fluorescent isotostandextran propagation in a platform is shown in figure H on the right side. Photosensitive nanomaterials change their structure when exposed to light. Light allows precise control over drug release with high spatial and temporal resolution. These materials are useful for targeting and imaging the tumors. Their response can be tuned by adjusting light intensity, wavelength, and exposure time. Light-sensitive polymers contain chromophores like azobenzene or spiropyrin that trigger drug release. Most of them respond to UV or visible light, which limits deep tissue use. Near-infrared materials overcome this by enabling deeper penetration and generating heat or reactive oxygen species to kill the cancer cells. Their mechanism include photoisomerization and photolysis. Azobenzene switches from trans to cis form, while spiropyrin opens its ring under UV. These systems are widely used in phototherapy and deep tissue drug delivery. Here in this image, the UV light triggered drug release into specific cells are schematically shown as seen in the figure B. Magnetoresponsive materials operate based on a fundamental mechanism. They can change their motion or orientation in response to an external magnetic field. This allows for remote control and precision guidance, making them highly useful in biomedical and diagnostic fields. Applications of magnetic nanomaterials includes magnetic separation techniques, for instance, in isolating specific cells or biomolecules. In cancer therapy, magnetic hyperthermia heats nanoparticles above 45 Celsius degree. This effectively kills the cancer cells without damaging healthy tissue. They also play a critical role in magnetically guided drug delivery, ensuring that drugs are transported directly to the target site. Furthermore, they are employed in immunoassays and widely used as contrast agents in MRI diagnostics. Production methods includes magnetic nanomaterials can be synthesized using a variety of methods such as hydrothermal processes, microbial synthesis, precipitation, and chemical vapor deposition. Other advanced techniques include laser pyrolysis and electrochemical synthesis, depending on the required size and magnetic properties. MRI contrast enhancement in magnetic resonance imaging works by aligning the protons in water molecules with an external magnetic field. To enhance the contrast of these images, contrast agents are used to increase the relaxation rates of water protons. While gadolinium-based agents are commonly used, their toxicity and low sensitivity have raised safety concerns. As a result, iron oxide nanoparticles are being developed as safer alternatives with higher signal-to-noise ratios, improving diagnostic clarity. For broader clinical use, these nanomaterials must be biocompatible, stable, and provide strong contrast. An exciting example is in 3D nerve regeneration, where magnetic nanoparticles are used to align collagen fibers for better tissue organization. This study by Antman Passing showcases how magnetic guidance can support nerve repair and regeneration by structuring the extracellular matrix. pH-responsive nanomaterials are designed to react to the change in pH across different biological environments. For example, while the stomach has a pH of 4 to 6.5, the intestine ranges from 5 to 8, while tumor tissues and infected areas typically show slightly acidic pH levels between 5.5 and 6.9. These nanomaterials are widely used in drug delivery, diagnostics, and wound healing applications. Types of pH-responsive polymers include the polyelectrolytes that undergo protonation or deprotonation, altering their charge in response to pH. Others contain acetyl covalent bonds, which break down in acidic conditions, enabling targeted drug release. In wound healing, pH-responsive silver nanoclusters are effective against infections caused by bacteria. Advanced tools like high UPS nanotransistors can detect organelle-specific pH changes functioning at pH values ranging between 5.3 to 6.9. Phototherapy and imaging applications as used with supramolecular nanomaterial, which is inactive under normal conditions, but becomes phototherapeutically active at pH values of 6.5. Similarly, melanin-like nanoparticles serve both in cancer targeting and fluorescent imaging due to their pH sensitivity. Chitosan, a natural polymer, shows positive surface charge in acidic environments and becomes neutral or negative as pH rises. Polylactic acid-based coatings, especially those loaded with resveratrol, release their payload rapidly at infection sites where pH drops down around 5.5 levels, preventing bacterial growth. Finally, nanodiamond coatings with zwitterionic PCBMA polymer enable enhanced imaging in acidic tumor microenvironments due to their strong pH responsiveness. This image illustrates fluorescence microscopy for HepG2 treated with PCBMA and nanodiamonds at different pH values as given in figure C on the right side. Redox-responsive nanomaterials are highly effective carriers for drugs, gens, and antigens in targeted therapies. They are being developed in various forms, including dendrimers, nanogels, polymeric micelles. These systems often include acid-labile polymers, such as polybeta-amino esters, polyanhydrides, and PLGA. Functional groups like thiols, platinum conjugates, thioethers, disulfide, and diselenide bonds enable controlled drug release under redox conditions. GSH is a natural antioxidant that protects cell from oxidative stress. Tumor tissues typically contain up to 100 times higher GSH levels than normal tissues. GSH can cleave disulfide bonds, triggering targeted drug release, specifically in cancerous environments. Disulfide-linked micelles disassemble in high GSH conditions, enabling precise release of anti-cancer drugs. Selenium-based carriers act both as prodrugs and responsive delivery vehicles. Hybrid nanoparticles with redox-responsive bonds offer regulated drug release inside the tumors. A GSH-responsive system was created using MAC-PTS, co-MAC-P, at silver nanoparticles loaded with comfotocin. Fluorescence signals change confirm drug release triggered by intracellular GSH values. The specific nanomaterials and their utilization in biomedical applications are summarized in this table. Sugar-responsive nanomaterials are designed to control insulin release based on glucose levels, making them vital tools in diabetes management. These systems often rely on glucose oxidase, which oxidizes glucose, or on lectins, which bind to glucose molecules. The oxidation process leads to a pH change, causing volume changes in the polymer, which in return regulates the insulin release. Acetylated dextran nanoparticles and ASDD nanocarriers have been developed to deliver insulin in response to glucose, incorporating both enzymes and therapeutic agents. Boronic acid derivative hydrogels have also shown promise as glucose-sensitive drug release platforms. Concanavalin A is widely used due to its multiple glucose binding sites, enabling controlled insulin delivery. In a notable study, Yin et al. Developed a pancreas mimicking system by embedding CON-A micro nanospheres in a polymer matrix, achieving long-term glucose-responsive insulin release. Enzyme-responsive drug delivery systems are designed using polymers or inorganic nanomaterials that respond to tumor-specific enzymes. These enzymes can cleave peptide bonds or acetyl linkages, enabling targeted drug release at disease sites. The most commonly used enzymatic triggers are proteases and phospholipases. Proteases are often overexpressed in inflammatory diseases, cancer, and infections, making them ideal for targeted therapies. For example, trypsin is secreted by the pancreas and plays a role in activating digestive enzymes. SPLA2 is highly expressed in tumor microenvironments, making it a key target in cancer therapy. It can trigger the degradation of phospholipase-sensitive liposomes, releasing drugs specifically in the cancer cells. A nanoplatform using the GFLG tetrapeptide enabled cathepsin B-mediated intratumoral drug release. ATP-coated silver nanoparticles were developed to deliver drugs specifically to liver cancer cells. For glioblastoma treatment, a protease-sensitive LMVP nanoparticle system showed selective tumor response. Another system incorporated urokinase plasminogen activator for targeted blood clot dissolution. The antibacterial activity on different implant surfaces after 1 week duration of implantation, having the enzyme-sensitive nanosystem is given in this image. Here, this table explains different stimuli-responsive nanomaterials and where they are utilized in the biomedical field. Well, this concludes my presentation. I would like to thank you very much for your attention and watching this video. I have provided my contact details here. If you need any further information, please feel free to contact me by phone or email or in person. Thank you again.